Chirikjian. I want you to know it took me a couple of years to learn how to pronounce his name. I learned that while I was in graduate school. Greg and I overlapped for 2 years. So if you read his bio, you'll see that in 1988 he graduated from Johns Hopkins. 1992 he got his PhD at Caltech. He didn't include it in that bio, by the way. 1990 is when we first met. So from 1990 to 92 is when I learned how to spell his name. Let's read his name. Also in the bio, you'll see lots of awards. He won the Presidential Young Investigator Award in 1993, and his work at Caltech started in snake robots. And for those of you who know me, you can only imagine the incredible impact it's had on my research, my group, and my students' research. So all these people who do a lot of this related work really have Greg to thank for inventing, I guess in the United States, the first hyper-redundant mechanism. So that's a term that actually Greg coined. So for all of you who are always curious where it came from this handsome young man here. He then took this work and generalized it in a whole variety of ways. He continued his work in robotics, in metamorphic shape-changing systems, but he also started developing some rigorous analysis in group theory and some applied math. In fact, he has 2 books. I only have one of them. That's because he didn't give me the other one yet. But it's a good book, and my students even today are. Oh, this is embarrassing.
No, keep talking, okay. Keep talking.
But he was also able to extend this work in studying how molecules, what was the word? Not molecules, is it different?
Proteins.
Proteins. Proteins are molecules, and know that. How they work together. So it's pretty incredible how he's been able to generate this breadth of research, and also an incredible amount of depth. In addition, he has done a lot of academic service. He served as the department chair of mechanical engineering at Johns Hopkins over 3 years. 3 of the best years of your life.
Well, you see how my hair changed color?
Right, and that's the other thing you should point out. We only we started only 2 years apart, and look what happened. Now he's continuing his service at the National Science Foundation, where he's doing service for our country in helping promote the robotics cause, giving us money, and all those other wonderful things. I think Greg can do a much better job describing his work than I can, so at this point I'm just going to sit down and give it to Greg.
Well, thank you, Howie. So you reminded me. I did not bring a copy of my new book as a gift, but I did bring you a little something from Baltimore. And just don't wear this in public. You might get beat up. So it's a Baltimore Ravens hat. So
it matches your book.
It matches the book. So I'll be talking about a number of things today, including stochastic models in robotics, but a number of other things also. I'm going to go way back in time to snake-like robots, talk about how that common mathematical framework that we use for snake-like robots can actually be used for non-holonomic vehicles, where instead of arc length as the parameter, we use time as the parameter, but it's the same concept. We'll get into that. Talk a little bit about spherical motors in medical imaging, hand-eye calibration, and robots that diagnose and repair and produce other robots. So, and this is all work that's been done with many collaborators over the years. Some of this work is new, some of it's relatively old, but for this audience it's mostly going to be new, I think, except maybe for Matt and Ralph and Howie and Mike, who've seen some of this before. From snake robots to uncertainty propagation in vehicles. So as Howie mentioned, I started my academic career building robots like this. And to show you how old I am, this was supposed to be a robot in outer space catching a Soviet satellite way back then. This was the land version of that. And the idea of this 30 degree of freedom robot was that it would have enough freedom that it could circumnavigate obstacles, do things like inspect power plants or do inspection tasks on assembly lines, things like that. And in fact, I showed these very same videos when I gave a lecture here. I think in 1991 was the first time. And so this is all older work. And these are simulations from those old days where we can use snake-like robots to perform caterpillar-like grasping and manipulation of objects, or to do inspection in moving obstacle environments like on an assembly line. So this is what I did in snake robots way back when. And then shortly after starting at Johns Hopkins many years ago, decades ago actually, we came to this concept of what we called the binary manipulator. The idea being that to make very inexpensive, lightweight robots, instead of using heavy, high torque motors, instead we could use pneumatic cylinders, which are very lightweight and have a very high payload to weight ratio. And the idea is with a pneumatic cylinder, instead of trying to control it in the middle of its stroke, drive it all the way to one end or all the way to the other end. So that's a binary actuator. And so if you make a platform manipulator out of these binary actuators, you get a 3-bit manipulator. You know, one binary actuator per leg, so a total of 2 to the third or 8 states, because you have 3 bits here. And we can take these binary actuated platforms and stack them on top of each other, and then you get something that looks like this in the planar case. Or in the 3-dimensional case, we can stack Stewart platforms on top of each other, each leg having binary states, or more than one. You could have 2 binary actuators to get a 4-state leg. And the point is that as you increase the number of bits, the number of states, the number of different shapes or conformations that the arm can attain grows exponentially, 2 to the n power. And so if you have a fixed base and you have this binary actuated manipulator and you attach a reference frame out where the hand is, then the hand will reach a finite but very large number of different positions and orientations. And so we called this the workspace density. And looking at that workspace density, we called it the crescent distribution. But people who do simultaneous localization and mapping have essentially the same probability density. They call it the banana distribution. Okay? And so it took us about 10 years to start reading that literature and realize that we were doing things that could be useful for them. And so we could use our modeling techniques in the same vein as what they were doing. Before I get to mobile robots and showing the relationship, I'll show this intermediate project, which is somewhat snake-like. It's a steerable, flexible needle. This was a collaboration with Alison Okamura and Noah Cowan and Robert Webster and a bunch of other students and postdocs from Johns Hopkins. The idea is that if you have a very flexible needle with a slanted tip, if you use that and stick it into a person, if a doctor tries to take that needle and hit a target like a tumor, the trouble is because of the flexibility of the needle, it will veer in a direction that's dictated by the bevel on the tip of the needle. And so the surgeons were viewing that as a nuisance, but Alison Okamura had the intuition to say, well, could we use that to our benefit? And she came to me, I don't know, 2002 and 2003, and asked, can we develop a model to describe the motion of this? And so I developed a kinematic model. It's a non-holonomic model that looks like this. So it's kind of like a kinematic cart or a steerable wheel, but moves in 3-dimensional space. And so with this needle, if you push the needle in, you can make the needle curve on a circular arc. And if you twist at the base, you can reorient the tip. So by pushing and twisting, you can actually steer this system in 3D. But the thing is, what we noticed when we performed experiments, and the experiments were not performed by sticking needles into people like a pincushion, but rather using a block of porcine gelatin. We would stick the needle in, because it's transparent, with the camera setup that was in the shared lab facility that we had. It was possible to trace where the needle was going. And so the needle wouldn't go the same way every time. there'd be slight deviations. And so we augmented the model with stochastic terms, and so we end up with a stochastic differential equation that describes random walks in pose as a function of time. And so these are Brownian white noises, so increments of Wiener processes, unit strength. This is a coupling matrix, and we were able to show with a very simple 3-parameter model on the noise that we could reproduce the range of different trajectories that this needle was taking. If we didn't have any noise here, this just says that the needle wants to follow a circular path with curvature kappa. And the G inverse G dot is a spatial velocity, and the V is like in the Murray-Lee and Sastry textbook for those who've taken an intro to robotics course that takes this velocity and writes it as a 6-dimensional vector. So now that's the spatial version, the 3D version of a non-holonomic vehicle like a kinematic cart. So if you have a kinematic cart, just like a wheelchair where each of the 2 wheels can move independently, and if you tell those wheels go straight forward and do dead reckoning, you believe you're following a straight line forward. But actually, if the wheels slip or there's a little bit of jitter in the motors, then you'll veer a little bit to the left or a little bit to the right or zigzag back and forth. And so that's adding noise to the wheel model, the non-holonomic equations of motion. Then you get a stochastic differential equation that looks like this. So this is sort of equivalent to a particle filter. And so if you could run this a gazillion times and get many stochastic trajectories and histogram up the end position and orientation, and you'd get this banana distribution. And that's often what's done in simultaneous localization and mapping. But another approach is to say, instead of simulating many trajectories, we can propagate the whole probability density, starting at the beginning where it's like a Dirac delta function where we know exactly where we are. The probability is concentrated where we know we are. That's our initial condition. And then we have a diffusion equation here. So this is like a heat equation that takes that initial Dirac delta function, and as you go forward, it melts. It diffuses out. Okay? Well, it turns out that this diffusion equation can be solved in closed form. And the reason why nobody observed that prior to us was that x, y, and theta are not the right coordinates to be using. Because when you use x, y, and theta, you get this banana distribution, whereas that's not a very convenient thing to express in closed form. But if we use what's called the exponential coordinates, then we get that the banana distribution in x, y, theta coordinates is actually a Gaussian in exponential coordinates. So we wrote this paper, the banana distribution is Gaussian, right? Now everybody says, wait a minute, it's not Gaussian. X and y, it's bent like this, it doesn't look like a Gaussian. But if you use a different coordinate system, then you get a Gaussian distribution in those coordinates. So I'm not going to go through all of the math, but that's what my new book is about. It's about how to do probability and statistics on Lie groups, such as the group of rigid body motions. What does it mean to define the mean, and what does it mean to define covariance, and how can these quantities propagate under convolution as you go along a path? The covariance spreads out more, and so this is a diffusion process that can be handled using ideas from probability and statistics. And together with my colleague Marin Kobalarov, we're looking at filtering algorithms that use these ideas to fuse priors, such as this dead reckoning model, as well as measurement models that also can be described using these banana-like distributions. So I'm going to move on. This is sort of a rapid-fire talk of many different topics, not in any great depth. But if anything interests you after the talk, you can send me an email and I can point you in the right direction to get more information. Topic 2 is a project that we worked on a few years ago, actually a decade ago, on spherical motors, and it's the relationship to medical imaging. So actually these two problems are actually the same mathematical problem. So we have some suite of mathematical tools that we use, and then we just try to tackle a number of different problems. So the first topic, subtopic here, is spherical motor and encoder design. So the motor that we designed many years ago, so if you want to design a stepper motor for rotation around a fixed axis, then the number of stator teeth and the number of rotor teeth shouldn't match so that you can commutate. And so what we did was to design a spherical motor where the number of stator poles, in this case these were electromagnets, and the rotor poles, which were permanent magnets, also didn't match exactly. They have to match enough that you can get alignment of two of them, but you want the others not to be aligned so that you can push things out of their local state, so that you can commutate. And so we came up with an icosahedral and a modified octahedral packing. So we ended up writing papers on how you pack circles on the surface of the sphere so that you could get different arrangements that were compatible between stator and rotor. But what's maybe more interesting is actually the encoder that we came up with. Of course, if you have rotation around a fixed axis, you can put your shaft encoder perpendicular to it. But if you have a ball motor that's rotating in all 3 degrees of freedom, where do you put your encoder? Well, we decided to paint the ball in black and white strips and put light sensors inside of the stator. And so the light sensors would see black and white, so you get a bit stream from those sensors. And we have a model, because we know how we've painted the ball, and in our computer model we could rotate and see when does that bit pattern click into place and match what's being observed. Well, it turns out that from an initial guess of the orientation, we could do gradient descent over the group of rotations. But this is a non-smooth function because a sensor goes from seeing black to white. That's a discrete change. And so we came up with a non-smooth gradient descent procedure for optimizing functions over orientation. And so this sort of shows the cost function, and this shows how jagged the landscape is, but that we could sort of lock into place and figure out what the orientation of the rotor was using this scheme. Now it's that mathematics and that computational framework is what carries over to this medical imaging scheme. By the way, there's many potential applications of spherical motors, including multi-degree of freedom ball and socket joints, or cameras, or you could have an array of them for moving parcels at UPS or in the post office, or you could use them as spherical motors for vehicles, spherical wheels for vehicles. By the way, we published this paper before the movie I, Robot, where they had the spherical spherical wheel cars. So that just tells you how old this is. But the other application where we used exactly the same mathematics was in a medical imaging problem where you have a patient. Typically, they use this for children to keep their heads steady in a CT or MRI scan. And so the idea is you have something called a head cage that basically they screw it down onto the person's head, and then the person goes into the imager, and then the imager takes slices, image slices. Now, if the person didn't move at all, they could just stack the slices up and get an image block. But typically what will happen if you put a child in an MRI machine, they're going to be squirming around, and then they take the head slices through, and because there was movement, you can't just stack those slices up. But then how do you merge those slices together? Well, it turns out that when you take the image slice through, you're also getting a pattern of dots where the image plane intersects this head frame. Okay? And from that pattern of dots, you can figure out what plane that image plane actually was. And figuring out what plane that was is actually a gradient descent procedure over the group of rotations and translations, SE3. And so we used essentially the same gradient descent procedure as in the spherical encoder for this medical imaging problem. So I guess one of the take-home messages from this talk is that, you know, if you really master a certain set of tools, analytical tools, computational tools, you can apply them to a variety of different topics. Okay, so another topic that we're working on, this is much more recent in the last couple of years, is hand-eye calibration for ultrasound sensor calibration. So the idea is, so ultrasound is a very inexpensive imaging modality. You can hold it in your hand. The technician moves it around. It's non-ionizing radiation. And what you get is an image in this ultrasound image plane. But the thing is, as the probe heats up or they squirt more gel and there's different conditions, this image is actually not physically attached to the probe. You can think of the image that's being created as something that can float relative to the actual physical probe. And so if you want to take that image information and act upon it, like use the ultrasound in one hand to drive a needle with the other hand, then you need to know how that image plane is actually related to the reference frame attached to the actual probe. And so this is where the ultrasound calibration problem comes into play. And it reduces down to a classical problem in robotics and vision called the AX equals XB problem. So here A, X, and B are all homogeneous transformation matrices describing rigid body motions. Typically you have a global tracker, like an electromagnetic tracker, that tells you where the probe is, a reference frame on the probe, relative to a global reference frame in the room. So that's, say, B sub I. And if you move the probe from position I to position J, you get B sub I and you get B sub J also. And then, so then from those you can get a relative motion, B upper IJ. And then, so what's often done is they construct what's called a model or a phantom for calibration. And this is just a crisscross set of lines. And in fact, we rapid prototype these, for example. And so we know what this object is to high precision. And so we put this in a water pool and basically take an ultrasound image. And we get, again, a intersection of that plane with this crisscross pattern. And then we move it to the new location. We get another pattern. And from those patterns, we know what the relative pose of this image plane is relative to the reference frame attached to this phantom, okay? But this phantom is not, we don't know where this is relative to the room, okay? But we don't need to know that either, because if we move from one location to the other, we can calculate the relative motion here, just knowing what this is and what this is, which we get from the shape of the pattern of the dots. So the bottom line is that we get this relative B information up there, Bij, and we get this relative information, Aij, and what we're looking for is the X here. What we're looking for is the transformation that it relates a reference frame attached to the image plane, which can float around in space, relative to a reference frame which is hard-coded onto the probe itself by, say, the electromagnetic tracker. And so if we look at this loop, this is A times X, and if you go the other way around, it's X times B. So we want to find the X that solves this equation. Okay? So it turns out, well, you go back a long time, 25, 30 years ago, people solved this problem under certain conditions. Namely, you have to have two pairs, A1, B1, and A2, B2, to get a solution. And those pairs have to satisfy certain conditions. Okay? So a little math here. So AX and B are elements of SE3, the group of rigid body motions in three-dimensional space. We're describing them as homogeneous transformation matrices. Every rigid body motion, this is very old, this is like, 200-year-old work. Schall's theorem says that basically every rigid body motion in space can be described as a translation along some line in space and a rotation around it. So that's called the screw axis. And so the distance d along the screw axis is the translational part, and the rotation is theta around that axis. And any homogeneous transformation can be broken up into these screw coordinates. So n is the unit vector, little n is describing the axis of rotation, and capital N is the 3×3 skew-symmetric matrix that encodes the same information as this unit vector. And so if we go back to the AX equals XB problem, there's a little bit of a busy diagram here. So you have two rigid body motions. So you have one with a screw over here and one with a screw over here. And to make a long story short, the only way that AX equals XB can have a solution is if the A and the B both have the same angle of rotation, the same theta, and the same d. Okay, so that's a necessary condition. And that has to be true if you have two pairs, A1, B1 and A2, B2. The A1, B1 has the same theta and d, and the A2, B2 have the same theta, d as each other. But also, you have these two screw axes, and there's conditions on them. If you have two pairs, they can't intersect, and they can't be parallel. Okay? And so there are these other conditions that need to be satisfied in order for AX equals XB to have a solution. And we use these conditions, we use these invariants of the group of rigid body motions, and actually pairs, so the direct product of this group, we use these conditions to filter out, because the traditional algorithms for AX equals XB assume that you have correspondence between the A's and the B's. But sensors can provide data at different rates, and you get a bunch of data over here for A's, and you get a bunch of data over here for B's, and they might not be synced. And so we have ways to sync that data when they're not synced in advance, using these invariants, because we know that the data can't match unless the invariants are the same. So we use the invariants of a Lie group as a filter to figure out how these data streams should match. And so this is relatively recent work. This is just saying what I said before, that the thetas and the d's have to match, and also there's other conditions on the angle and the distance between the screw axes has to match. Okay, so I'm going to move to the next topic, which is very different in many ways, and in some ways the same. It uses some of the same mathematics, which is modularity in manufacturing and autonomous field robots. So that seems like a pretty broad topic. So there's work that my former student Matt Moses did for his PhD on a modular manufacturing system. And so this is essentially an XYZ, so this is much more recent work, okay, than some of the others. This is a modular manufacturing system. So it's an XYZ platform. It's made out of bricks that we actually cast ourselves in molds out of plastic. And so this whole robot is screwed together, okay, like Lego blocks. And it can do XYZ maneuvers. I'll show some videos later. And the point is that given a stack of parts, like the parts that the robot is made out of, this robot can go and do pick and place and screwed operations and actually assemble a copy of itself. Okay, so we call it a self-replicating robot. Okay. So here are what some of the different parts look like. There are motor modules, and there are structural modules. There are guides and gears and various things. I'll show you in the video. It'll become much more clear what the ideas are. So where's the science in all of this? Well, if you go back to 1984, which was, I think, the first ICRA, Art Sanderson from RPI published a paper on what he called parts entropy. Okay, and Matt knows about, you have a question about parts entropy?
He was at Carnegie Mellon.
He was at Carnegie Mellon. Yes, he was at that time. So, and so the idea of parts entropy is that, so if you have an assembly line, let's say you throw parts down at random, then those parts are going to have a certain joint distribution of positions and orientations. And a measurement device like a camera will reduce that entropy because it will give you knowledge about what the positions and orientations of those parts are. Well, we're taking a different tack, which is to say if you want to mate two parts, then designing those parts so as to reduce the parts entropy can assist. So for example, if you want to insert a peg in a hole, actually that's Matt also, right? The Lozano, Perez, Taylor, Mason in a different order of authorship, that paper going way back. So if you want to insert a peg in a hole, it has to be you have to be straight on. But if your hole is conical and your peg is a cone, then you have a lot more freedom to be wrong, and as you insert, it will self-align. And so we design our parts so as to overcome this sort of parts entropy. So we have, in each part that we have in our robot, the bottom has a conical hole and the top has a conical peg, so that the robot doesn't have to be very sophisticated and it can still mate the parts. And so we did an analysis of what is the probability distribution that you can be off by, how off can your poses be, and you can still mate the parts reliably. So this is related back to the parts entropy idea. So I'll show videos at the end. The next topic that uses the same idea of sort of probabilities in pose is teams of mobile robots that diagnose and repair each other. So the idea is this. So I like modular robots. So we have a team of modular mobile robots. So there are 4 parts in each of these robots. And so if this part breaks down, it's easy in principle for another robot to come in and take that out and put a replacement part in. But first, if the team is autonomous, they have to decide amongst themselves which robot is not functioning correctly. And then how do they make that decision? Well, the idea is if you have, say, n robots, then n minus 1 of them can be watching one robot. That robot can go through a little diagnostic dance, like move your gripper up and down, do a figure 8 pattern. We're going to watch you, and we're going to see how well your performance is relative to the nominal performance that we expect. Now, of course, there's going to be some noise to be expected, so this is a probabilistic assessment. The actual path that's observed is the path, but the sort of normal behavior is described by a time-evolving probability that's nominally along that path. And so what we can do is we can do a maximum likelihood calculation of assessing the path, configurational or conformational path that the robot executed relative to the probability of trial runs of what normal behavior looks like. And we can do that not only for normal behavior, but we can a priori simulate all kinds of different fault modes. And we can, so then the robots can collect information, pool their information in a Bayesian setup, and ask the question, what is the most likely state of this robot? Is it healthy? Is the left wheel burnt out? Is the gripper not working? And then, after they've made this diagnosis, if the robots are mechanically designed to be modular, then the team can go in, swap out a module, and swap in a new one. Or if they assess that, well, this robot is too far gone, this is broken, this is broken, this is broken, then they can cannibalize it just for the parts that they know are working right. Okay? So that's the idea here. Okay, so it's like in the middle, it does its little bumblebee dance, they collect information, and then they make an assessment. So this is not all cartoons. We're actually designing and implementing robots, lab prototype kind of robots, NSF-style robots, not DoD-style robots. Maybe the CMU version can come next. The real robot version, this is the lab prototype version. So we have a central hub. We have 6 modules that are, they look like a sort of a snowflake. And we have a specialized kind of gripper that will insert into another module and work together to lock it or unlock it. It's because you want to easily be able to attach or detach these modules to their hub. And so we do a combination, on the one hand, sort of computer science work with the diagnosis, and on the other hand, mechanical design in terms of how to make the modules modular so that they're easy to assemble and disassemble. This is just a cartoon showing the process of how to lock in and take a module out. I have some videos I can show of this, and we presented some of this at an ASME conference earlier. And we have a number of papers published in this area, both on the theory and in the implementation. Let's see how I'm doing. Okay, so I'll speed things up a little bit so there's time for some videos. The final topic that I'll mention that we work on, which is very different than the others, is applying robotics ideas to model biomolecular motions and interactions. So the idea of proteins as machines. So for example, this is a ribbon diagram model of a protein called lactoferrin, which is found in milk. And so what happens is if an iron atom attaches in here, then it changes conformation. And so the idea of proteins as large, complicated, high degree of freedom systems that react to the environment, change their shape, dock with each other. It's kind of like grasping or, motion planning. It's all related. And so we do modeling of these motions. These videos were made by my former student Moon-Ki Kim, who went back to Korea as a faculty member and has been very successful there. In fact, he has a server set up where biophysicists can enter any two shapes of a given protein and he'll make a movie for them. So he gets lots of hits on that. And has become very popular that way. So I'll say the conclusions now, and then I'll show a bunch of videos. So our lab does a lot of different things, including mechanical design. I'm in a mechanical engineering department, snake robots, spherical motors, modular reconfigurable robots, etc. We do a lot of applied mathematics, like in those books, image processing, medical imaging, what I call information-driven motion in robotics, including these sort of self-diagnosis schemes. But also you could imagine other schemes like trying to infer the intent of an actor, whether it's a robot or a human, from the trajectory that they're executing. And many of these topics involve very similar mathematical tools. Whether it's probability densities on Lie groups or the invariance, it all sort of comes back to this sort of group theoretic and differential geometric view of the world. And now I will show some videos, if I can get to the right place. Okay. So I may have to drag this over here. Okay. So this is showing this you could call it a modular manufacturing system, or if it's building itself, it's a self-replicating robot. If it's building something else, it's a modular manufacturing system. So we certainly don't have Ralph Hollis's level of precision in these, but our goal is to make relatively simple robots that can do complicated things. So these are parts cast out of plastic. They do have these conical pegs and holes, and so it's very easy to pick and place parts. And the end effector, so I'll show some other versions of this. The end effector has it's a combined wrench and screwdriver at the end of it. And so the screwdriver is a female part of a screwdriver, and then each part has actually a threaded screw sticking up. And so if you want, we pick up parts by having this screwdriver actually latch down onto the part, onto the screw fixture of the part, pick it up, bring it over, drop it down, use the conical setup so that the parts can be reliably put in place. Then it unscrews. Then the wrench part of the same end effector comes down and then actually latches it tightens a bolt down. So from a set of stacked parts, those stacked parts could be all screwed down into a block of parts. This robot can pick up parts from the stack, place them down, and create a copy of the original, or create any combination of parts from that initial set. It doesn't have to be a copy of the original robot. It could be something else. So we've constructed little cars and things made out of the same parts. So, another part of this problem is to ask the question, how complicated does a robot have to be in order to be able to reproduce itself? Right? So if you think of a very simple robot, then there's far less to do to make a copy of it, but then is the simple robot able enough to make a copy? And in fact, other questions like, what does it mean to self-replicate? Well, if you have a bacterium sitting in a soup of nutrients, yes, it can self-replicate. If you have a person on an island and they only have sand to eat, no, they can't self-replicate. And so what we came up with, and then of course there's Hodge-Lipson's cubes, and so the question is, how do you define whether something is self-replicating or not? And the answer that we came up with is that that's the wrong question. The question is to say, what is the degree to which something is self-replicating? It's not a yes or no question. If you have something that's made out of 1 billion parts, and that thing goes and assembles each of those 1 billion parts, then into a copy of itself, you might say, well, yeah, that's convincingly self-replicating. So that's the direction we're going, is a robot that can assemble relatively simple parts into a functional copy of itself. And so why do you say, well, who cares about that? Actually, the reviewers of my grants say, who cares about that? So, but if, if one wants robots to be harvesting materials in outer space and whatnot, a self-replicating paradigm, I think, makes a lot of sense. And that goes way back prior to me. Gerard K. O'Neill talked about these kinds of things way back. But this actually gives, and also Robert Freitas, there was a report, a NASA report from the late 1970s that sort of said the same thing, but they didn't actually have a physical instantiation of the concept. Okay, so this is an actual physical demonstration that it is possible for robots to assemble parts to make a copy of itself. And combined with things like 3D printing and other technologies, the sky's the limit. Okay, so I'll show, let's see, I don't seem to have the other videos. Let me see. Oh no, okay, that's the wrong thing. We're doing things with 3D printing in irregular domains. So here it shows the self-repair idea. So here this robot autonomously is coming to this. It's not doing the diagnosis. This robot is sort of sitting there dead in the water, and this robot is autonomously locating and extracting a module, and then it's going through this procedure that I mentioned before, involving the two tools. So it extracts it, and then here's the autonomous.
Hey, Greg. Would that not be viewed as a self-reproducing, self-replicating robot?
I would call that a self-repairing robot.
I mean, can it not go further? I mean, you can pull one out and put one in.
It could, and it could. So actually, I think I'll finish there, but then I'll take questions because I think time is short. But yes, you could. But that comes back to the concept of the degree of self-replication. So if you have 6 modules, and you ask how much effort went into designing and building each of those modules compared with the amount of time and effort that the robot is doing to do the insertion, I would say that more time went into designing the modules than the robot did. So who gets credit, the human or the robot? And if you can give the robot more credit, then it's more self-replicating. And if you give the human more credit, it's less self-replicating. So we're calling that we're calling this an autonomous self-repair procedure. But you're right, if you had the initial hub sitting there and then the robot added modules, you could call that self-replicating, but sort of like with low degree. You might call it degree 6 because the total robot is sort of 6 times more complicated than the individual parts. You just add 6 parts together. But if you have something that has 100 units or 1,000 or 1,000,000 units, and the robot has to do all of these operations to put it together, and if each of those units could be constructed by squirting a little plastic into a mold and then the robot picks the part out, then that would be a much higher degree of self-replication. So, you know, where you draw the line between self-repair, self-replication, self-assembly, or replication without being self-replication, there's a lot of syntax there that needs to be navigated. So with that, I think I'll just conclude and say thank you, and I'm happy to answer any questions. Matt?
So do you have a way of measuring the complexity of one of these modules so that you can answer, so you can address those?
Yes, we wrote a paper about that. So we have 2 measures, well, 3 measures. So one measure is this degree of self-replication. The other is the degree of complexity. And the third is sort of the degree of reliability. But okay, so let's address the complexity issue. So you have a robot. It's made of structural elements. It's made of actuation elements. It's made of computing elements. Okay, so then how do you reconcile all of these things? Well, the way we reconcile it is to say, 2 relays are equivalent to a bit, basically. You can transform that into the most basic logic unit, a gate, let's say. And so you can relate electromagnetic coil complexity, so that the basic elements in a relay, to the most basic computing elements. Now, so if you have a microprocessor on there and it has whatever, millions, billions of gates on it, then zoom. That's by far the most complex component. And if you say, well, I'm going to tack a wheel on here and I'm going to tack a Lego block on there, then the amount of value added by this assembly process compared to what went into designing and constructing the computer it's nothing compared to the computer. So what we've tried to do is to distribute the complexity over the overall system so that every module is relatively simple, and so that the amount of work, let's say, that the robot is doing compared to the work that went into building the blocks or the units is so that the robot is doing much more of it. And we do have a quantitative measure for assessing that.
Follow up on that. If you're sort of breaking up the complexity into maybe 6 more equally balanced things, but each of them are still have a microprocessor maybe that's not quite as powerful, it still seems like the complexity of each piece is just as high. I don't know why the balance between a really complicated computer with a simple wheel attached as opposed to 2 more balanced modules.
Well, we were actually breaking things down so far that the motions that you saw here could be replicated without using any computer. We could use actually relays. So we could use a system of relays, and that system of so a relay could actually be reproduced from in situ resources, right? So you could cast molten metal, make a core, you could cast coils, so you could actually make from scratch every element necessary to replicate some of the behaviors that you saw here, which were relatively simple. So we're not doing it that way, and maybe that's not a smart way to do it, but just if you want to be a purist and say, yes, you could do everything from scratch, you know, reducing it down to that level is, you know, is something that we've looked at. I mean, an alternative, you know, if you wanted space robotics to reproduce, there's the vitamins approach where you say, okay, send the microprocessors. We're not going to count that in the mix in terms of the complexity because that's lightweight and practically speaking, you could send those things.
So bricks are a wonderful idea. If you figured out how to make bricks, you can make all kinds of wonderful buildings. But in the end, there are limitations. There's some compressive strength, and you can make buildings bigger than this. They have no tensile strength. To make really interesting things, you need a wide range of materials and processes. And this is why I'm always skeptical about all these ideas of I can make a whole bunch of identical parts and then make anything out of it. Would you speculate on that a little bit and see where that goes?
So the first thing I'll say is that these are not only bricks, like Lego bricks that you just stack in, where we have screws that we actually twist into, so there is some tensile strength. In terms of, well, I think rapid prototyping is sort of a game changer in terms of how much of the job should be assembly and how much of it should be fabrication. And so we've sort of partitioned into two parts. Is you know, we're using sort of old style fabrication of casting in molds, but much of this could be 3D printed, and then novel materials could be used, and you know, how much of this could be, you know, like the RepRap is a, you know, actually that RepRap paper appeared in Robotica, so please send your papers to Robotica. I'm the editor-in-chief there, have been for the last 10 years. And that RepRap paper is one of our most highly cited papers. I'm not the author, I'm just the editor. You know, in terms of how much, if we have an XYZ platform, how much of it could have just been 3D printed rather than doing the assembly? You know, that's a valid question.
And then even there, you start to run into the same kinds of problems. You have one kind of material that you're 3D printing, well, maybe you have multiple nozzles with different materials, but ultimately you can't do interesting heat treating kinds of things that you really need to do to really strong, high performance devices, parts.
Right. Well, it depends what your application is. And again, the killer application for this in space application is if the choice is you have a lower than high performance robot doing assembly and sort of patterning the surface of the moon rather than astronauts with shovels, then, you know, it might have value in that way.
And with enough processes, you can make anything out of sand.
Well, it's not only sand, but also nickel, other meteorite materials.
I hate to change the subject, but I was wondering, the probabilistic diagnosis is very interesting to me. I wonder if you could talk a little bit about the advantages of having the multi-robots versus just a single robot doing more observations.
Right, so a question often I get is, okay, so your robots are diagnosing each other and repairing, but what are they actually doing that's useful, right? So you could imagine having the robots work together to move a large, heavy object that one by itself couldn't. They could be working together in construction. They could be working together in reconnaissance. But the point is that the current paradigm is that, you know, whether you have a single robot or multi-robots, if the robot breaks down, you know, it's out there.
That wasn't my question.
Oh, okay.
The question was, from a diagnostic point of view, what advantage do you get from having multiple robots observing the robot?
Oh, okay. Well,
versus a single robot observing the other robot, which I think is a great idea.
Okay.
But I'm just wondering the advantages you get having multiple robots doing that diagnosis versus one robot doing the diagnosis, since since it's going to get, the other one's going all the way around, it's going to get a view of everything anyway.
Oh, you're saying one robot actually navigating around taking multiple, as opposed to having multiple.
You said the robot that's broken.
Yes. Does its little dance, right?
So it exposes all of its components.
Right.
Each to the diagnostic robot.
Right.
And so the question is, what advantage do you get by having multiple robots view versus one robot view the complete camera?
So I guess there's two answers to that. One is that sensors always have noise, and so noise suppression by having multiple observations from independent sources. That's one. And then the other is that you don't know that the robots doing the observing are actually functioning correctly. So that's another kind of level of noise suppression, is that you have an outlier and its camera isn't producing the right data, and that outlier the effects of it can be suppressed by having sort of a crowdsourcing amongst robots. So that's kind of two different aspects of the same thing, which is noise suppression by having multiple independent observations.
The other side of the coin, though, is that now you've got the added complexity of having to integrate the information from all the other robots.
That's true. But I guess the scenario in which this is sort of cast is that these robots are already working together in some cooperative task, so they already have the communication protocols in place to do their day job. This is just what they're doing in their off time, is to diagnose each other.
So I have a couple of small questions. So going in order in your talk, the first one was when you were describing the spherical encoders, I was curious, how did you just figure out what the patterns, those black and white patterns should be on those balls? It seems to me that you solved the problem. Given a pattern, tell me what the motion is, but... Right, so I'll tell you what you don't do. You don't make them regular. You don't paint them as if they're the surfaces of an icosahedron or dodecahedron or cube, because then you have ambiguity up to the discrete symmetry subgroup there. So what we did was we experimented, and my collaborator Ed Scheinerman at the time said, well, why don't we randomly put points on the sphere and generate Voronoi cells and color some of them randomly black and some of them randomly white, and let's see what happens. And then my former student, David Stein, who was the lead author on those works, was experimented with triangular patterns, and we just sort of cranked through and asked the question which ones had higher resolution, because of course it's discrete, so you're always going to have you have a finite number of light sensors, and you have these finite regions that are black and white, so there's going to be some jiggle room in terms of orientation that will give you the same bit pattern. So the resolution of the encoder depends on the placement of the sensors, and it depends on the shape of the regions that you choose. So it was a trial and error process. I can't say that we have a scientific method for the design of those patterns. Okay, thank you. So my second question is, this is a quick kinematics question. So when your AX equals XB, or to get
Yep.
So you had said at one point that A and B have to have the same axis of rotation?
No, the same angle and the same distance along the axis, but the axes themselves can be different.
That was my question. Okay. I heard axis, and I was trying to figure out.
It's the rotation around the axis and the translation along the axis have to be the same for both, but the two axes themselves can be different.
Okay, beautiful. And then the last.
Okay.
Can I just follow on that?
Oh, please, please.
So, going into your theme of probabilistic models, because of noise, you don't actually want them to be equal. I mean, they're not necessarily going to be equal. Is that correct?
Right. You have a threshold.
So that was the question. I mean, what kind of is it just a uniform bound on the equality? Did you do some kind of probability distribution? How do you actually do that?
Right. So the way that we did it in this particular paper, which we presented at ICRA in Hong Kong, 2014, was we had a sort of a constant bound and we use that for the filtering. But we have we have a number of new methods that we've developed for AXXB, including what we call the batch method, where you don't have to have any correspondences between the A's and the B's. You take all of the A's and you put them in one big point cloud of poses. And you take all of the B's and put them in a separate cloud of poses. And then the X has to match this cloud to that cloud, and that can be formulated using actually this concept of mean and covariance of probabilities in pose. We basically match the covariances and the means of these two clouds, and that gives us the X very rapidly and very robustly. You could have points missing from this one that have no correspondence in this one, and the method will still work. So we have methods that handle noise, handle shifts in data, lack of correspondence, etc. I just presented because this was a sort of a broad overview of different topics. I didn't go into depth in the AXXB, but we have a number of different methods that we've developed there.
Thank you for seeing that.
Oh, yeah.
See it back when I speak out.
Thank you, thank you. So I think we've dragged everyone through questions long enough. So why don't we thank our speaker. Before we pull out, just one announcement. We have the post-seminar reception honoring the 4 new faculty. It's going to be over there. And does it start now or does it start at 45 minutes? Oh, so you have to figure out something to do for the next 10 minutes. So we'll see you. We'll see you over there. If you walk slowly, it'll take 10 minutes to get there. All right, now let's thank our speaker.